Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. It is hard to believe that TWIMLCon AI Platforms is just over a month away. Join us at TWIMLCon to hear from industry luminaries like Shopify's Solmaz Shahalizadeh, Netflix's Faisal Siddiqui, and BP's Fran Bell on what leading organizations are doing to increase the efficiency of developing machine learning and deep learning models and getting them into production. Learn about the practices and platforms being put into place by companies like Google, Spotify, Intuit, and more. And engage with fellow data science, machine learning engineering, platform engineering, and MLOps practitioners and leaders to share, learn, and connect on how to accelerate, automate, and scale machine learning and AI in the real world. Information and to register, visit twimlcon.com. Before we jump into today's episode, I want to send a huge thanks to our friends at Amazon Web Services for their support of the podcast and sponsorship of this year's reInvent series. AWS offers a vast array of machine learning services and supporting cloud infrastructure, putting machine learning into the hands of every developer, data scientist, and expert practitioner. Its extensive set of ML services at all three layers of the technology stack offers a broad array of capabilities, including contact center intelligence, DevOps tools, industrial machine learning, enterprise search, health analytics, and much more. And Amazon SageMaker, one of the fastest growing services in AWS's history, helps data scientists and developers to prepare, build, train, and deploy high-quality machine learning models quickly by bringing together a broad set of capabilities purpose-built for machine learning. To learn more about AWS ML services and how they're helping tens of thousands of customers accelerate their machine learning journeys, visit aws.amazon.com/machine-learning. And now, enjoy the show. All right, everyone. I am here with Edgar Bahilo Rodriguez. Edgar is a lead data scientist in the Industrial Applications Division of Siemens Energy. Edgar, welcome to the TWIML AI podcast.
Thank you, Sam. I'm very glad to be here.
I'm really excited to chat with you. You spoke at reInvent this year on productionizing R workloads using SageMaker. And we'll be digging into that as well as a number of other topics, interesting topics that we'll be digging into. But before we do that, I'd love to have you share a little bit about your background and how you came to work in machine learning, industrial machine learning in particular.
Yeah, sure, Sam. I'm Edgar Bahilo Rodriguez, now lead data scientist at Siemens Industrial Applications, as Sam mentioned. And as many other engineers, because I'm an engineer myself, a former energy engineer, I learned how to code by accident. And then I was doing my bachelor thesis in electricity price forecasting. So it was when I started with the classical and more traditional time series models, ARIMA, exponential smoothing, and so on. And then after I did my master's, I was focusing a little bit more in optimization, mathematical optimization. And at the end, machine learning is yet another mathematical optimization problem. You just need to minimize some sort of loss function according to different algorithms or using different methodologies. And it was after this master that I started to focus more into the area of machine learning, especially in time series forecasting again. I joined Siemens, and there I started with some of the most classical tasks that you do at the beginning of your career, like some ETL, some data warehousing. And then we started to build a lot of prototypes, POCs, using machine learning, starting from, as I say, forecasting, but also clustering, some NLP and computer vision use cases. And the pile of prototypes started to fill up quite quickly. And it was this year when we started our journey in MLOps and when we are starting to set up the architecture or the infrastructure required to really scale up analytics in industrial applications.
Awesome. It may be helpful to have you talk a little bit about Siemens Energy and your division and what your focus is. Siemens is a huge company that does a lot of different things. I'm imagining all kinds of use cases relating to, IoT and wind turbines and things like that. But what is it that you actually are working on there?
Yeah, that's a great question, Sam. Siemens is a very big company, but now we are Siemens Energy, a spin-off of Siemens. So we are roughly 91,000 employees, and we are divided into five main divisions. The one that I'm working on is industrial applications, which is roughly around 18,000 employees. And then we have, as you mentioned, the wind power that is called renewables. Traditionally, it was Siemens Gamesa. Then we have the generation business. They are taking care of the big power producers as well as of selling solutions to decrease the environmental impact of already pre-existing installations, either Siemens or non-Siemens. The transmission colleagues that they manufacture transformers or any other kind of hardware that connects the energy system. And then the new energy business, which they work with electrolysis, power to X, hydrogen cells, and yeah, basically the guys that they are trying to enable the rotating equipment to run with hydrogen or alternative fuels. And in industrial applications and distributed oil and gas, which is my division, we basically service any kind of industrial equipment that you can think of. So we work with gas turbines, medium gas turbines, small gas turbines, aeroderivatives, gas turbines, reciprocate engines, turbo compressors. So the portfolio is quite huge. I will not say that is endless, but we have a big segment of the market in industrial applications, I will say. So we cover quite a lot of products.
Awesome. And with that in mind, you shared a few of the use cases that you worked on in your reInvent talk. Can you kind of review some of those key use cases for us for machine learning?
Sure. We have four main use cases that they push us to the cloud directly. The first one was the sales and operation and planning prognosis engine, which I covered it in detail in my reInvent talk. So basically trying to forecast some operational KPIs that they are driving or service intervals for our machines. So as an O&M producer, we need to service the machine, bring new components, inspect and replace the components that they are damaged to enable the safe operation and the most reliable operation of this industrial equipment. We have also the dispatch optimizer, which is an external customer-facing application where we are using machine learning to forecast electricity prices, the power demand that the power plant is going to face, the fuel prices, the maximum available capacity of each of the units, because this is a parameter that changes quite a lot depending on the ambient conditions. And then we use all of these forecasts to pre-schedule the operation of this machine. So we are trying to help the customer to deal with the uncertainty of the liberalized electricity market. So how to bid, when you should go to a spot, when you should stick to your power purchase agreement. So a little bit of an optimization problem with machine learning on top. Then we have the data-driven sales. That is not a classical machine learning use case, I will say. We are trying to simulate the operational gains in terms of efficiency and, of course, decreasement of environmental impact when we do an upgrade of one of our machines. So we have some surrogate models of the efficiency and emissions of these machines that they have been created using machine learning. And then we try to estimate the impact of the upgrade based on the historical running profile of the machine. And then finally, we have the probabilistic design use case that this is I will say a statistical use case is not a machine learning use case per se, but we need to analyze a huge amount of data because we are looking to many sensors, many turbines, actually the whole fleet, different components. So we are crossing a lot of data. And all of these four use cases, they have in common that this time series the main data source. And because of the nature of time series, which is usually a lot of them high frequency, high volume, we actually needed a better platform to run this kind of analytics.
Well, so maybe this is this is going to be a dramatic oversimplification, but it sounds like at least for a few of those use cases, there's at the core, you're trying to build models of the machinery that your customers have out in the field. And then from these almost predictive maintenance types of models, you have different products. One is focused on, sales forecasting. One is focused on dispatching. One is focused on helping the customer optimize the way that they schedule their resources. Is that the right interpretation for this?
So, I mean, we are a hardware-based company, so the models that we have for, let's say, predictive maintenance, they are what I will call white box models. So thermodynamic models that they give us very good accuracy. When we are using machine learning is when we are trying to predict parameters that they are very hard to predict. This could sound like an oversimplification, but there is no white box model behind the electricity prices. I mean, of course, at the moment of the settlement price, you can try to find a way of calculating the electricity price if you know what is the output of each of the generation technologies in this country. You can try to make a more physical or maybe even electrical driven model. But when you are trying to predict, when you in the future, when you are trying to forecast, you need to refer your predictions to information that you have available a priori. And precisely in these variables, they are, I will not say stochastically by nature, but that they are very hard to predict with white box models is where we are using machine learning. So in the other areas of our business, we have our thermodynamic models and our white box models where we have very deep expertise.
Got it. Got it. And you mentioned that the models are all based on time series data. You also mentioned that that's where you started, earlier in your career. Talk a little bit about the, both kind of the evolution in the way you've personally worked with time series data and some of the approaches and challenges that you see today in working with time series data. How is machine learning, deep learning, all these things change the way you've approached things since the early days?
Yeah, that's a very good question, Sam. So, as I mentioned at the beginning, I started with the most traditional approaches for time series forecasting.
ARIMA and the like.
ARIMA, exponential smoothing, or maybe linear regression. And of course, doing some clustering based on the internal features of the time series, like, for instance, the seasonality, the trend, these kind of things. But machine learning has come with a lot of strength into the time series field, I will say. I think that there are three main, let's say, key takeaways from the incorporation of machine learning and deep learning in your time series models or in your time series use cases. Looking into machine learning, we have different kind of supervised learning algorithms, like clustering algorithms specific for time series. So we have, for instance, dynamic time warping to calculate distance similarity between multiple time series. And then we can cluster this distance using different kind of clustering algorithms that they can give us maybe another kind of information that the clustering with traditional internal features of the time series they can give to us. It is true that, for instance, the TW is very expensive to compute, but still I think that there is some value there. The second thing that I think that machine learning and deep learning they have bring into the time series field is that most of the libraries or tool stack that it was available so far,
Most of
for
the
instance, the
libraries are
forecast
what?
package, a very famous R package, it was designed to make one step ahead predictions. Meanwhile, machine learning has enabled different kind of forecasting strategies. So, for instance, the direct forecasting strategy, where you have different models per horizon, and you optimize your models based on this horizon. Also, it has enabled the multiple input-output strategies. So to have one model to forecast multiple horizons at a time as well, without using recursive forecasting. And I think that also, especially now that machine learning and deep learning, they can help you with time series that they are highly nonlinear, that maybe they have very high frequency, for instance, or very complex interaction between the time series itself. Machine learning and deep learning, they can help quite a lot if what you want to do is to build one model to rule them all, if you want to call it like this. So instead of trying to build, for instance, a vector autoregression model, you can try to input multiple time series to an LSTM neural network and to predict multiple time series as an output. So this one model to rule them all, I think is a concept that is important. And I think that we only need to look into the M5 forecasting competition to see the results and to see that this, if I recall correctly, this year, the winner or the best approach. It was a combination of machine learning, traditional time series, deep learning, and a lot of ensembles on top to make different aggregations by, I think it was a store country. I will have to check the details, but this aggregation of information, this combination of the knowledge of each of the individual time series, I think that is something that you can do only with machine learning and deep learning.
And so, as you have kind of evolved the way you approach these problems to incorporate machine learning, there are a couple of interesting things that have come up for you. One is the fact that you use a mixed set of technologies to actually build out these models. And then I think hand in hand with that is the way that you architect systems around these kinds of models has changed. Can you, talk a little bit about maybe that, we'll start with that latter point and then, work our way to the mixed technology. These use cases that you describe, the sales, dispatch, the simulation, and the probabilistic design, are these online or offline, interactive systems, and how is all that kind of driven a set of architectural decisions for how you make them available to your users?
Good question. So, I mean, especially in the field of model serving, I mean, you basically have two main approaches to serve predictions of your model. Either you do it on batch mode and on demand or in a scheduled basis, or either you have a REST API endpoint to hit your endpoint and get the predictions whenever you want. But in the use case that we are facing, the data usually comes in batches, even that it comes quite frequently with 1 day or less. Every 1 day we receive data, and even actually faster. We do not have this necessity in principle for the moment in these use cases to have REST API endpoints as a serving. But even so, what it has changed is that if you want to have a full pipeline, you need to change a little bit your way of thinking, because of course you can schedule this pre-processing for calculating your features, doing the training, making the predictions, and then store the predictions in somewhere S3 or a data warehousing. But if you do it like this, in this pure schedule basis, you will not be prepared for what is coming next. And with that, I mean that you should always try to look for event-driven architectures. So you should put, for instance, some lambdas on top that they trigger certain processes every time that you receive new data, because then you are absolutely sure that if your data frequency changes from once per day to once per hour, you are covered. There is no issue. The workflow will run. It will just run accordingly to the new data that you are receiving. So I think that first, the event-driven architectures are very important. The second thing is that, of course, we have time series, and we have a lot of time series. So you could have multiple ways of approaching this problem. Either you try to adapt parallelings as much as you want, so kind of divide and conquer strategy, one very small model for every time series, or either you take profit of what I mentioned before about these neural networks or more complex techniques that they can deal with multiple time series at a time. Independently of what you choose, you need to be aware that it will be certain challenges. So if you go with one time series per model, you will have very small models, very fast inference, but also you will launch a lot of containers. So you can maybe hit your account limits. If you go with one model to rule them all, maybe you end up with a model that is 20 gigabytes or even more. So you end up with a model that is very hard to serve. So if you would like to put this into a REST API endpoint, the endpoint will be extremely expensive. So I think that that's the main things that you need to think about it, or that it has changed in organization, the way of seeing things, that depending on how you are going to approach the problem, you will have certain advantages and certain disadvantages. But if I will have to choose for one, I think that what we have learned is that independently of which pattern you take, you can probably do it in an easier manner than you imagine at the beginning. At the end, AWS is providing quite a lot of technologies. And of course, you can build from scratch, but you also can build on top.
Mm-hmm. Mm-hmm. Yeah. So all of these decision points that you were elaborating on has kind of led you to develop a strong viewpoint about kind of the future of the way folks think about these applications and the a specific role of ML architecture or system architecture and the importance of that. We talk a lot about data scientists, we talk about ML engineers, but this architecture piece is really important to you. Elaborate on that and some of the ways that you've seen that play out in your business.
Yes, sure. So I think that this kind of roles that you described, data science, MLOps engineer, machine learning engineer, machine learning architect, they come with the maturity of an organization. So traditionally, organizations tend to have data scientists that they do a lot of POCs, and with this POC, you kind of can generate like a lot of expectations. You can build very complex and very accurate model. But usually, when you try to integrate this between in your applications or in your business process, the challenges or deployment and operationalization they start to appear. And then is when the MLOps or the machine learning engineers they come into place, and they try to fix not the issue, but they try to put his small piece of sand in the ocean of machine learning to help us to build our systems. But the problem is that independently of what you are going to deploy or what model you have built, I think that architecture should come first, because it's true that maybe you need to do some exploratory data analysis, some quick modeling, some understanding if the data that you have is sufficient, is good quality or not. But you should always try to design whatever you are doing with the mindset of, okay, maybe not this year, maybe the next year, maybe in 2 years, this becomes a very important application. This becomes part of a bigger system. And I think that is where architecture comes into place, that you need to define the requirements of how you should deploy things, define the requirements of how you should write code, because that will help you to go to production faster, and that will help you to create value quite much more faster than if you don't have this setup in place.
Yeah, it's funny the way you put that. It reminded me of a saying that we used to have at a former, a kind of a past work life. We were building these systems that were designed to be very scalable, and we would run into situations all the time at enterprises that built some app thinking it was a throwaway app, and it would become what we call unintentionally mission critical. Like it would get introduced in some business process and get built on, and all of a sudden you have very important systems relying on something that was never designed to be, mission critical. And what you're saying is, if you go a little bit further and engineer it right from the beginning, or architect it right from the beginning using principles like event driven, then you can have a higher level of comfort that if that does happen, you don't end up in a bad spot.
Correct. I think that it's also important to understand that not every company has like thousands of data scientists or thousands of machine learning engineers. At the end, machine learning is just becoming part of the toolbox that companies they can use to solve problems. But these companies, they have their core businesses, and they have process to support, customers to support. So I think that a good architecture from the very beginning will help everyone to maintain and sustain these applications. Of course, now talking from the machine learning powered based, but also other applications. And that I think is going to become key, because with time, machine learning is becoming more and more accessible. We are starting to have AutoML. We are starting to have a lot of high-level APIs to very complex algorithms. And I think that we should expect that in the next year, machine learning will become more and more common. So I think that the next challenge will be a part of the operationalization also in the architecture side of these things.
Mm-hmm. So one of the interesting aspects of the way you do machine learning at Siemens is that you do have these mixed technologies that you use to build models. Some of your use cases are based on R, others are based on Python, others are mixed. Can you talk a little bit about that and the challenges that it introduces for your workflow?
Sure. Yeah, I think that Siemens Energy is a very big company, so there are a lot of people programming in different languages. We have software developers that they prefer maybe .NET. We have data scientists working with R, with Python. We have maybe statisticians that they work only with R. or we have pure data scientists very specialized in deep learning that they only work with Python. And this, yes, could present a challenge, but it also depending of how you approach that. Because at the end, it's just code, isn't it? The important thing is to have your code decoupulated. The important thing is to build software according to best practice. And right now, pretty much you can build any code with Docker, or you can build Docker containers that contain any kind of code, and you can build containers in R, or you can build containers in Python. So, I mean, that's not, I don't think that it could be a potential issue, but if your team has become aware that there are these kind of best practices, I think that you will be able to succeed, or you will be able to avoid the wallet of the interoperability between the two languages or three languages.
Mm-hmm. Yeah, this is one of the areas that has changed in a huge way over the past, I don't know, 10 years or so. When I talk to technology companies that were trying to enable machine learning 10 years ago, the big challenge was that you'd have these statisticians, before we were even talking about data science, right? That were building these models in SPSS and R and SAS and things like that. And then they'd throw them over the wall to someone who had to like code them from scratch from, C and C,
Or Java.
not even really Python, Java.
Yeah.
And a lot of companies came around just to try to bridge that gap in one way or the other. And now with today's technology, what it sounds like you're saying is that it doesn't really matter. Throw it into a container, have some known entry points, and just let your hopefully your MLOps system is container based and can just deal with whatever you throw at it. Am I getting that right?
Yeah, I think so. Of course, there was some challenges at the beginning. So, especially in the R ecosystem, we got the version 1 of Plumber quite recently. That is to write REST APIs natively in R.
Okay.
Before, of course, you could do it as well, but I know that there are some teams outside Siemens that they were wrapping R code into C++ or writing the interface in Scala, which was surprising to me, but it seems that it's a common pattern. Okay. No issues with Scala. Is know that I didn't know what people were doing around this.
Let's not get the Scala fans going.
No. But the thing is that the language also evolves, or the languages and the packages also evolves in the same way that the let's say cloud technologies, they are evolving. So just to put you an example, now in Lambda recently it was announced that you can run containers in Lambda, always that they are less than 10 gigabytes if I recall correctly. So that also enables the possibility of maybe running R in Lambda, which by default is not possible. You need to write your custom runtime. And I think that, this is going to be more and more common, that we will have new languages, coming into the play. But overall, the whole enterprise sector is becoming more and more professional with this kind of good software practices. And the cloud providers and AWS, they are making this easier for us. So I think that at some point in the future, maybe this language discussion, C++ versus Java, I don't know, R versus Python, Rust versus Go, I don't know, maybe this hopefully goes away.
You've mentioned Lambda a few times, and serverless is a technology that has come up, I think quite a bit on the podcast, but not a ton. And Lambda is AWS's serverless technology. I'm wondering if you can maybe elaborate on some of the ways that you use serverless and Lambda in your workflow and your pipelines.
Sure. So usually you use machine learning. The common use case that I see of the Lambdas is, of course, to run inference if your model is very small. If you have, for instance, a TensorFlow model, it could be a little bit challenging because of the 3 gigabytes layer limit. Now this went off, so probably we will not have this issue anymore. But it's quite common to use Lambda, or I think it's even compulsory when you are going to configure a step function workflow. So a step function is the orchestration layer of natively from AWS. Even that now, before reInvent, I think that they also announced the support for managed Airflow another workflow scheduler. But basically, in the step functions, you configure the payload of your step functions with a Lambda. That could be one of the use cases. And also you can use this Lambda to inject hyperparameters into your training jobs. So if you are going to, for instance, run a complex pipeline where you have multiple algorithms, depending on the event type, is this is, for instance, SGT or, I don't know, random forest, then you could load one set of hyperparameters and then send it to the training container. So I think that will be the common pattern of the usage of Lambda in machine learning. And also another common pattern would be to fetch maybe the results of the hyperparameters. So imagine that you have, I don't know, 5 different algorithms: ElasticNet, SGT random forest, an LSTM neural network, a support vector machine, and you have launched hyperparameter tuning for each of these 5. So if you want to select the best of the best, probably you will have to use a Lambda, because the hyperparameter tuning job will give you the best support vector machine, the best SGT boost, the best random forest, the best so on, so on. But if you want to select the best of the best, either you persist in database or you can maybe fetch it with a Lambda after the training process is finished.
And just out of curiosity, for a while, one of the, at least in the early days of Lambda, one of the challenges was that you'd have these kind of separate artifacts, functions all over the place, and it was a little bit difficult to kind of manage them as a unified system or code base. Are there tools that you're using now that are making that easier to do, to integrate Lambdas into a larger system architecture?
That's a very, very good question. The Lambda rabbit hole. So if you have thousands of microservices that they are built on Lambda, I agree you could have an issue. Of course, we always try to keep things as simple as possible and to do it project basis. But it is true that if you want to join or to harmonize and have governance of all of your microservices, and you have all of your microservices implemented in Lambdas, this could be a challenge. I am not an expert on the topic, but I know that some people is putting GraphQL on top of Lambda to manage the microservices. I know also that there are some companies like Uber that they have very interesting approaches to their microservice management, and Netflix as well. But in the stage that we are for the projects that we have not come with that issue, at least not yet.
Okay, so it still can be an issue at certain levels of scale, but if you're, even at the level of what you're doing, you're not really running into it as a big blocker. Cool. So are there any unique aspects of the kind of industrial nature of the problems that you're trying to solve that have come up for you?
Yes, they are. As I told before, we are a hardware-based company, and we have a lot of knowledge of how machines work. So with that means that we know exactly what can cause a machine to go wrong. And we can see that in any of our, let's say, thermodynamical calculations that we run on top of the sensor data, or the ones that we have for our digital twin. So as a, let's say, hardware-driven company that it has so big knowledge into these white box or physics-driven models, when machine learning comes into play, people want explanations. So explainability, I think that is a very big topic, especially in industrial sector, because at least at Siemens Energy, it's not only that we service the equipment, we also design it from the very beginning. So we select the materials that they are going to go into the components. We put all of the components together. We make the designs. We manufacture. Then we service it. We sometimes even help with the operation, and we also repair also sometimes the components that we have manufactured. So people really want explainability in this field, I will say. Another challenge that I will say is that this field is very new, and when you have had something that has built with years and years of experience, when something so new comes, that especially comes so fast, you can be a little bit hesitant to adapt it, especially because you have in-house solutions that they are working very well.
Mm-hmm. Yeah, and one of the topics that, or themes even, that has recurred in some of my conversations in the podcast, especially with folks in the research side, is there are a bunch of efforts to try to fuse kind of physics-based models and statistical models together so that they're not these two separate islands that aren't informing one another. Are you doing anything on that front, or have you found anything that that works and is easy enough to use? A lot of what I've seen is on the research side.
No, we are working on that. And again, the fact that we are a hardware-based company, that doesn't mean that the statistics was in our DNA. I mean, at the end, any kind of component that we design, we evaluate the risk of failure. For instance, this has played a big role into an organization. And of course, I mean, I will not like to simplify or oversimplify machine learning to statistics, because all of us here, we know that this is not true, but this is closely related. So what I'm trying to say is that we are working into that direction. We are working in enhancing our digital twin that is thermodynamic driven with also some machine learning technologies. There are still nowadays some calculations that they are very expensive to do, like for instance CFD simulations, and we think that
The computational fluids, or the
fluid
CFD.
dynamics, correct.
Okay, CFD. Yeah.
Yeah. So when we are trying to simulate the temperature profile that a plate will have and so on, the simulation is very expensive. And we think that there is potential to use machine learning to either speed this simulation or to either maybe make a surrogate of these simulations that can run very fast and is good enough. So we are working into that direction.
And maybe going back to the machine learning and architecture part of the conversation, we started talking about your talk, which is like productionalizing, operationalizing, and all that kind of brings up ML ops and that operationalization element. Any interesting things to say about the kind of that pure operationalization part, keeping this up in production, monitoring it, managing it over the long term? What have you learned there?
Well, what we have learned is that we need to manage it automatically because we have many models. that that is probably the first takeaway. I mean, of course, you can have one person approving and so on, but depending on which kind of approaches you take, you really need to automatize this process. I talked at the beginning of the conversation about that you can have, for instance, one small model for every time series, or you can have one for all. So if you have a lot of time series, then you have a lot of models to supervise and monitor. So I think that one of the lessons learned is that you need to automatize as much as possible this process, but you also need to be able to trace back anything that fails. I think that that was one of the main takeaways. So model registry, proper CI/CD pipelines, and code versioning is very important. And also, I think that from the, I will say, challenges of the MLOps side is traditionally the model monitoring approaches that we have seen. They are what I call passive model monitoring. So
Meaning
you
what?
usually, meaning that you usually schedule a monitoring job that is checking the data that you have receiving and that you use for training. So you need to schedule this process. And if you detect a deviation between, let's say, the two populations, then you will trigger a retraining. But that doesn't necessarily mean that your model is going to underperform. So what we call active monitoring strategies, which is based on a current prediction error, is something that we think that is cheaper to maintain, because you will only retrain your model when you really need it. It is true that to have this feature drift or population drift calculation is useful for explainability purposes, but we think that active model monitoring is the way to go.
This active monitoring, is this something that you've had to build yourself, or is this something that the platform gives you for free, so to speak?
So this is something that we have to build ourselves, but is one of the new features that you will find into SageMaker this year. So if I recall correctly, now it's called model metrics monitoring. It's in the new version of the documentation. So I strongly suggest to everyone using SageMaker that goes to the new documentation and see for the new changes. But yes, we had to implement it from scratch, especially for our use case that was time series based.
Mm-hmm. And the key idea there is that you're monitoring the drift. Is it with every transaction as opposed to in larger batches, or is there a different approach you're taking?
It's an event-driven workflow. So every time that we receive new data, we calculate the features that we need for inference, or that we need to make the time series predictions. And then when we have the predictions that we did last week or last day, we compare with the data that we have received. So if this data that, of course, the problem with time series is that you cannot compare when you are predicting, because you predict and then your data gets received with some lagged time, I will say. So you need to wait until you receive the new chunk of data. And if you forecast for instance, the next day, you might have to wait 1 day. If you forecast for the next 1 week, you will have to wait 1 week, and so on and so on. So if you use a direct forecasting strategy, this could become very, very complex.
So the idea is that based on this event-driven paradigm that you described earlier, you build from the very beginning. As soon as you get data that would allow you to compare your predictions, you have a process that automatically does that prediction, and that's the active part.
Correct. So the active part is that every time that you have received new data, you compare it to what you forecasted previously, and you do it whenever you receive this event or this new data. And then based on that, you decide if you go to retraining or if you still make predictions.
Got it. Awesome. Well, Edgar, thanks so much for taking the time to chat with us and share a little bit about what you're up to. Very cool stuff.
Thanks.
Thank you.
Thanks, Hans. It was a pleasure to talk with you. And thanks to Imari for sending me the invite.
Thank you. All right, everyone, that's our show for today. To learn more about today's guest or the topics mentioned in this interview, visit TWIMLAI.com. Of course, if you like what you hear on the podcast, please subscribe, rate, and review the show on your favorite podcatcher. Thanks so much for listening, and catch you next time.